Welcome everyone. This is Yusuf Shaili, membership chair in ISA Oman section. And let's kick off our PACO week, where PACO means the process automation and control optimization. In this week, we will be hosting three amazing sessions for the process automation and control optimization, where we'll be talking about practical control strategies in process industries. And tomorrow we will be talking about advanced process optimization using APC and RTO, real-time operation. Then we will close out this week with a session about AI, predictive analytics, and smart plants. We will be hosting three high-achieving engineers from different entities, starting with engineer Omar Al Bahdoor, a senior process control engineer from OQ Base Industry, and engineer Khalid Al Amri from Oman LNG, then engineer Abdullah Al Msalhi from Petroleum Development Oman. For those who are new to ISA means International Society of Automation. This society has different divisions, whether from the aerospace, automation, or the cybersecurity. So we have 16 divisions in total where our focus is, and almost 2,900 members per division. Going on, ISA has different geographic sections all over the world. So these professional sections are distributed for the country. So we have 103 sections on 33 countries, 14 global districts, and plus 200 student chapters all over the globe. In Oman, we have ISA Oman section. Our section is very diverse here. Sorry, I think you can hear me now. Our members are from different companies, entities, and also universities. You might spot your company or university from this. By the way, this is a collective logos. We might have members who are whose company is not showing here. However, we have reached 140 members in total this year. So Ethraa is a series of webinars where we host professionals, students, to showcase their projects, to perform a knowledge sharing through Zoom and online sessions. And today's session is a continuity of what we have started back then. Also, as a member, you will be having access to ISA Publication Hub, where we have multiple books, Connect Live, conferences, standards, papers, and training modules if you are interested to have one. Also, we provide a view to ISA standards, whether in OT cybersecurity, control and automation, valves, instrumentation loop diagrams, and intelligent devices management. You will have access to all of these documents. You might scan the QR code now in order to connect, to engage in technical discussions, to network with professionals, to grow and explore the opportunities, and to learn from what we have here and what we offer with ISA. You can find out more about us from our social media channels, whether in LinkedIn, YouTube, Instagram, and X. We made it easy for you. You can just scan this QR code and it will take you immediately to those. So, waiting to see you as an ISA member. scan this QR code to take you to the membership page. Moving on to our first session today, we will start about a session about practical control strategies in process control industries. By the way, if you have any question, you can drop it in the chat box, and I can direct it immediately to the presenter. However, the the verbal questions, will be allowed only once the presenter finishes his presentation. So we are happy today to host Engineer Omar Al Bahdoor, a senior process control engineer from OQ-based industries. Engineer Omar is experienced in process control and plant operation and commissioning. He has a strong background on APC, Advanced Process Control, DCS, SCADA system, and performance optimization. He has contributed to major industrial projects, whether from designing phase to commissioning and startup. He is expert in process safety, hazard, cell studies, and operational reliability. He is focused on improving plant stability, efficiency, and continuous performance enhancement. Today, Engineer Omar will be presenting about practical control strategies in process industries. Engineer Omar, welcome to the show.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you, Yusuf Shaili, for the nice introduction, and thank you all audience for attending and sparing the time to attend this valuable session. Yusuf, if you can just allow me a couple of minutes, because for somehow I got some issue with my slides. A couple of minutes and I'll be back, okay?
And now, engineer, take your time. So meanwhile, we can go back to this. Become a member today. Come on, guys. We will be more than happy to see you. And if you have a question until the technical issue gets resolved, please drop it in the chat box, and we will be more than happy to support and answer your question. So I have here Engineer Nasser Al-Alawi also as a host. He is the ISA Oman section president. He will be reading the chat box, and if you have any question, please feel free to ask.
Thank you, Yusuf. Just for until Engineer Omar become ready, can we know, from the attendees by show of hands, if you can just use show of hands, how many of you are process control professionals, or you are working with this as a discipline, or at least you was working for process control?
Okay, so we have a hand here. Two.
Oh, only two, huh? Then I think it will be more interesting, really, knowledge sharing that you will, for people who are not from the background of process control, definitely you will learn something new, inshallah, with Engineer Omar. How many of you are working in the oil and gas industry?
Again, the same two. Okay, so we have also student members here, and Khalid Al-Amri didn't know how to raise his hand, but we are counting you, Khalid, with us.
Khalid, Isa Al-Belushi as well. Thank you, team. We have also among the attendees some of the legends of process control. I will not name them. Let them be, shown as a guest, but they are a legend. It's really an honor to have them here to be part of this session, and for supporting, I say Oman, and I say members as well. So thank you, Mr. Unknown, Mr. Guest.
So again, just giving you a glimpse on the week. Please be noted that tomorrow we will be hosting Engineer Khalid Al-Amri, a lead process control and automation engineer, where he will dive deep in process optimization using advanced process control and real-time operation. The day following, which will be Thursday, we will be hosting Engineer Abdullah Al-Msalhi from Petroleum Development Oman, where he will also share knowledge about AI, predictive analytics, and smart plants. If you have any question related to ISA or to PACO Week, please feel free to drop it in the chat, and we will be more than happy to answer it and support you if you have any issues.
Yusuf, I'm good now. I can start.
Then we will move straight forward to Engineer Omar Al Bahdoor. Omar, the floor is yours.
Let me share the screen. So the screen is visible now?
Yes, it is visible.
Assalamu alaikum all, and sorry for being late. Had some technical issue. So our discussion today will be about PID controllers, PID system. As you see from the title, from PID to plant performance. And maybe to begin with, sorry, this slide is not available, but for people who is not familiar with the PID controller, so what is a PID controller and why we need it? So a PID controller is like a control algorithm that automatically adjusts the process at the desired value, and it works based on the error. And why it is needed? To optimize the plant, increase production, and to have more safe operation. If you can see in the picture here, the plants before PID controllers were running on manual intervention. You can see on the right side, here's the operator. He is adjusting the valve to have, and here's the furnace. Okay, so he's looking to the gauge, and based on this temperature, he will open and close the valve, and this is the fuel valve. Okay, so for example, I have a low temperature on this valve. He will open more fuel gas to have high temperature on the furnace. Okay, and vice versa. If I have a low temperature, a high temperature, I will close the valve. And as an operator, he's a human, so of course he will forget. He will open more, he will close more, or he will just leave it as it is because he's busy with other activities. So mistakes can happen. Losses of fuel, which is dollars, can happen also. You can see here after implementing the PID controllers, the same furnace I have, okay, and I can see the value in this controller, and the control valve will be manipulated by the controller based on the error. I have here my set point, 85. I have here my process value, 84.9. That means I have 0.1 error. So to adjust and to correct this error, the controller will manipulate the valve to open and have more fuel to make it 85. And this is happening in seconds. And the operator, of course, he will take maybe some time, and the valve, some valve takes some time to open and close. Okay, so why we need the PID controllers? If you can see in this diagram, this is the comfort zone. And normally without PID controller or with a bad PID controller, okay, we are operating the plant far away from the optimum set point. For example, I have a compressor, and this is a refrigerant compressor, for example. To refrigerate and to condense more product, I have to increase the speed. On the other hand, I have a constraint. One of these constraints is motor amps. You can see here, for example. So the controller is having a high variation. Okay. If I increase the speed, it may touch the high limit and trip the plant. So that's why we always run the plant on the comfort zone, away from the optimization set point, which is near to the constraint. Some of the terminologies that we need to understand is our CV, which is the controlled value. If we go back to the previous example, here, our controlled variable is the temperature, which is produced as a result of burning this fuel gas. Okay. Our MV, which is our manipulated variable, is our control valve. So the controller is controlling the controlled value, temperature, by manipulating the control valve. So this is our CV. It can be flow, temperature, level, pressure, whatever. And then we have something called MV, which I already explained. Typically, it's the valve, fan speed to cool down or whatever. So this is also the manipulated. And then we have our DV, which is disturbance variable. And this is something very important. Disturbance variable will have the same effect of manipulated variable. It will affect our CV. The main difference, I don't have control on it. The MV, the controller is manipulating it to have our desired CV. But the DV is something like, for example, by nature. If I go to the previous example, let's say I have an ambient temperature in the summer, which is very high. Okay, so this ambient temperature is our DV, which affects the tubes here or equipment here, but I cannot manipulate it. It is because of the season. It's because of the wind, because of the rain. I have no hand on it, but it plays a crucial role in our system. So here we will take this example to see the characteristics of the valve and the PID controller, and how you can see the effect on the real plant. Let's say I have a valve opening at 55%, okay, and I have a flow 1000 kg per hour. So as we mentioned before, this will be our MV because it's a valve manipulated variable, and this is our CV. I step test. Step test means I increased. Okay, I increased the valve opening from 55 to 58. So this will be the effect on the flow. It will increase gradually. Of course, if it is well tuned, okay, it will increase gradually to reach the desired value. Okay. From this diagram, I have to understand the important terminologies that it is used in the process control. So we call it transfer function. You can say transfer function parameters. Okay. One of them is process gain. So what is process gain? Process gain is difference in our CV, current CV value, and previous CV value divided by difference in our MV. So you can see our current MV value is 58. Previous one is 55, so difference is 3. Our current flow is 1015, previous one is 1000, so difference is 15. So process gain is 15 by 3, which is 5 kg per hour. So why this is important? By this process gain value, I can understand that 1% opening in the valve, it will give me an effect of 5 kg in the flow. And this is something very important for all process control engineers, technicians, and control system guys. So that before they work on, try to optimize the controller, tune, anything, they should understand if I have a very high gain, that means it's very sensitive. So I can make it very aggressive. If I have a very low gain, if I have a very high gain, that it's very sensitive, I should make it less aggressive, and the opposite. And then I have something called dead time, and dead time is something like you can say nature in the controller. So when I change the valve position from 55 to 58, if you can see here, there's 3 seconds with no change in the CV. This is our dead time, and it is also very important to understand. And then there is something called our time constant. Okay, and later on I will explain that mathematically time constant, we represent it as a tau and dead time as a theta, and this is used in the tuning also. So what is time constant? Time constant is the 63% of the change. If I say that here I have reached to my desired value 1015, so it is 100%. So 63% of the change is our time constant, and it's 12 seconds. Then I have there is other terminology that's important also: a direct action and a reverse action valve or controller. So as it is mentioned here, if PV flow is higher than SP, decrease PID OP. Okay, so if flow increased, more than the set point, so I will close the valve. The valve will be closed. This is a reverse action controller. Okay, flow increased, valve will decrease. This is a reverse action controller. Okay, and here in this example, if flow increased, if the level increased in the tank, the valve opening will increase. This is direct action. And again, open loop and closed loop. So open loop is nothing than the manual mode. So because many people misunderstand these terminologies, when I have an open loop, that means PID controller has no interaction in the loop. It's doing nothing. It's only the operator. And the closed loop, that means PID is controlling the loop. PID is on. So all the effect of proportional, integral, everything exists. Okay, then here we have something called error. As we mentioned, that PID controller is nothing than a control algorithm that automatically adjusts the process. This adjustment is based on error. If there is an error between the process value and the set point, then the PID effect will come, because it's based on error, and we will see this in the algorithm. How we calculate the error? Basically, people say it's PV minus SP, but how DCS and PLC system understand, they understand in percentage and in PV range, and this is very important. So error is equal to PV minus SP divided by PV range into 100. Why this is important, and we have seen this a lot in many plants. Some people, they will say that controller is not working properly, performance is very, very bad. So they will ask for tuning. So one of the most important things before you tune the controller is to check whether you have the correct range on the instrument or no. Okay, you should have the correct range on the field and on the DCS, because this equation exists in the PID algorithm. So if range is correct, if range is wrong, okay, is not correct, then your error is not accurate, and then your PID action is not accurate, and then your PID performance is bad, and tuning will never help you. Okay. And here's an example. Like, for example, let's say we have a temperature controller, and the range is 100 to 500. Our current process value is 300 Celsius. Our desired set point is 200. So from the equation, PV minus SP, that means this PV 300 minus SP 200, divided by our range 500 minus 100, which is 400. And we multiply into 100, then we have 25% error. Okay, so this is how the PID controller understands it. Sorry. So what is P, I, and D? So P is a proportional action. Okay, so proportional action is the level of aggressiveness. How aggressive, how fast is your controller? You want it. Okay, so level of aggressiveness. So if I want my controller to be fast acting, I should have more proportional action. Okay, and in some DCS, like Foxborough and maybe Yokogawa, we have something called proportional band. It's nothing than 100 by the proportional. Okay, so we have PB, so 100 divided by P. This is the proportional band. So of course, always we need the controller to be as fast as possible, but sometimes you cannot make it fast due to sensitivity of the loop. The loop is very sensitive, and you cannot make it fast. And integral shows the level of impatience, how much the controller is impatient. Okay, and it can be represented in seconds or minutes, and this is very important because in some DCS, when you tune, if the I integral is in seconds, that means this is very, I mean this is very small number. If it is a minute, then 2 minutes it's 120 seconds. So you should first see the unit, okay? Because sometimes it's in seconds and sometimes it's in minute. So what integral do in the controller? It repeats the proportional action. So proportional makes the controller very aggressive. Okay, it repeats the equation. If I have error, then I will repeat the correction action. So aggressiveness of this correction action is the proportional action. Repeating of this aggressiveness behavior, this is integral. How much I should repeat? 1 minute, 30 seconds. And derivative is level of anticipation, expectation, prediction. And I'm not sure if I have mentioned here in the slides. Yeah, so normally in the plants, we use P and I. So D is not used normally. Maybe used in some temperature controllers, but typically it's P and I. And how you can understand the effect of derivative. Let's say you're driving in a hill and there is a slope. So in the beginning of the slope will be very sharp, right? So you will push the throttle full, okay, to achieve to reach 100 kilometer per hour, for example. So as you go, the slope decreases. So that throttle, full throttle that you have pushed, comparing to the slope resistance, it decreased. And that same throttle will increase the speed more than 100%, and you want it only 100%. So the car will fly maybe. If you keep on the same throttle, the slope is getting decreased till it is flat. So till you reach the flat street, maybe the car will fly, or you will reach 140 kilometer per hour. So derivative anticipates the change in the error. Anticipate. So before I reach to the top of this hill, I will slow down. If the magnitude of error is high, I will need more action. If it is lower, I will anticipate that I'm reaching my set point. So decrease the throttle like this. And here you can see the PID controller algorithm. And this is something we call equation B. And it is the most common equation. Sorry. So how this equation, maybe just fast I can explain it. It is our OP is output. It is our current output. I mean, the current or the new output, how you will get this value, how the controller will get this value actually. It will take the previous output plus proportional, and then it will multiply in the difference change in error. And this, if you can see my arrow, this is our proportional gain. This is our proportional effect. Okay, this is our proportional gain. And then plus error into difference in the time by integral, and this is our integral plus the derivative. Derivative is the change in the change of rate of the process value. So if PV is not changing, D will not change. Okay. Yes. So you can see here, proportional contribution acts on change in error. Okay. Why this is important? Let's say you have a controller and bad performance, and you want to tune. So there was some high variation, and you've tuned the controller, and it became flat, almost flat. And you think you have done a great job, and the controller performing fantastic, okay? And that's not true, because you have to do a step test to check your PID parameters, because you have the PID parameters that you have adjust. It was for that scenario, and you haven't seen the proportional action, because error is not changing. It became flat. Error is not changing. So to make an error, change the set point to make a disturbance, then see the proportional action, whether it is oscillating, whether it is overshooting, undershooting. So always before tuning, do a step test. After tuning, do a step test. Okay. And this is our integral contribution, and this is our derivative, as we explained before. And yeah, you can see this node, proportional band. As I said, in some DCS systems, it is not proportional. It is proportional band, PB, which is nothing by than 100 by P. So in proportional gain, as you're having high number, it is more aggressive. Proportional band, as you're having lower number, that's more aggressive. Okay, so it is the opposite, but it's the same action, just how manufacturers are representing. Yeah, and you can see here, as we mentioned before, transfer function parameters, our dead time, as we mentioned before. So no change in flow for some time. So when you do a step change, when you open the valve or close the valve, maybe for 5 seconds, 10 seconds, some slow loops can be in minutes also. So the valve, I mean, you will not see any effect. So you should not think that controller is not performing. This is a natural characteristics or property in the system, in the loop, in the controller. Okay, and that time you can also call it time delay. So that time we can represent it in mathematically as theta, this symbol, Greek symbol, and time constant, as I explained, it is the 63% of the desired value. When I do the step change, if from 100 kg to 110 is 100%, so for example 107 is 63%. So this is our time constant, and we represent it mathematically as tau, this letter, this symbol. And then we have something called process gain, as we mentioned before, and it's very important. It's the change in flow, CV, divided by change in MV, which is normally the valve. And this we call it first order transfer function. And we have something called zero order transfer function, or we call it integrating loop. So in this zero order transfer function, for example, I have a tank. Okay, I am filling this tank with 1,000 kg per hour of water, and this valve is open and it's taking 1,000 kg per hour of water. I have this level indicator showing that 45% level, and this is my desired value, for example. So if I open, let us see here. Yeah. So flow is 100%, as we said here. Okay, in this FC, it is 100%. I decreased the flow from 100 to 90. So what will happen, because I'm closing the valve here and same amount 100 is coming in, you can see the level will start increasing without stopping. It will increase 45 to 75 and to 100%, and then it will overfill. Okay, so it doesn't have something called TTSS, time to steady state. It doesn't have steady state. It is an integrating system. It will just keep on increasing since you haven't adjust the valve. And in this zero order transfer function, we don't have a process gain. We have something called ramp rate, which is same as process gain, but we call it ramp rate. And to calculate it, you will have to take change in level before, like it was 45, then 75, and change in time, which is 15 minutes, and we divide it by the flow, change in flow, yes, which is 10. Then we get our process gain for the zero order, which is ramp rate. And this is very important also to understand that in this system, if I open the valve 1%, I will get 0.2 change in the system. So here is some common problems in PID controller. So if you see this behavior, some people say it's cyclic, okay, wavy, but it is an oscillation. It is a continuous oscillation. This is the set point, and this is the process value. So the system is oscillating. It's never settled on our desired value. Continuous cycling. So and this is, a thumb rule, but again, practically things are not 100%. We cannot stick to this 100%, but it can give you some reference. It can give you some hints where to troubleshoot. So if you see this behavior, typically this is because of high proportional or low integral or both. Okay, if I have a very high proportional, as I said before, proportional action makes the controller fast, and always we want it to be fast, but too much fast is not very good. It can make it oscillate. Okay, maybe 5 proportional gain on this valve, on this system, will make it steady, and the same 5 on other loop will make it oscillating. Okay, so from system to system, it will be different. So if I have a very high proportional number, it will oscillate, or if I have a very low integral. Okay, very low integral, that means it's impatient. It's repeating frequently, consistently, the proportional action. I have case 2, persistent deviation. It keeps on dropping, going away from the set point. It's not able to reach the set point. And this is typically because of low proportional or high integral or both. If I have a very low proportional, the valve, the controller is very weak. It's not aggressive. Okay, so it cannot reach the desired set point. And one more thing I need to highlight, that maybe previously I put a proportional parameter, and it was wonderful. Okay, the system was stable. After some time, it is giving this behavior. It's not able to reach the set point. One of the reasons which can any logically be is the valve condition. We call it stiction, valve stiction, sticky valves. So as valve are getting aged, okay, getting old, they are sticky, especially at certain opening, certain range of opening, they are sticky. So this thickness needs more proportional. Though it was before on the same proportional, it was good, but it was new valve. But when it become old valve, I need more proportional. Okay, I have case 3. You can see too long to reach new set point. It is very slow. It is reaching the set point, though it is taking more time. Okay, and you cannot accept this in the industry. Okay, that means you're losing something. So this can be because of low proportional and high integral, or both. Here you can see it is, I made a step. It is overshooting. Okay. Now overshoot is less and less and less till it is settled. So it is oscillating, but not the same as this one. This is like consistent, frequent oscillations. But here oscillations are initially big, and then they are getting smaller till they settle to the set point. And this can be because of high proportional, low integral, or both. As we explained, common problems in the industry, oscillations, people call it hunting, cycling, instability, all the same meaning. Sluggish control, which is slow control or weak. And I always advise people based on what we have seen, based on experience. If a system having low performance, people will always call the control engineer or post control. Okay, what we have to do to investigate, diagnose, to check whether it is a controller issue or other issue, because in a lot of cases it is not a controller issue. It can be a valve having a problem, valve issue, old valve, sticky or whatever. It can be an instrumentation issue, whether it is physically damaged or having wrong range. Okay, it can be even logic, some logic issue, and we have seen in the industries. So we have to investigate and sit with the operators, speak to them, and try to understand whether this is a controller action or other action, because other actions other issues you cannot solve them with the tuning. Tuning is only for bad performance of the controller, not to solve valve issues or instrumentation issues. So I think this is already explained, causes of oscillations. Sorry. Then one of the tuning methods. So there are a lot of tuning methods. Okay, there is trial and error, and this is the most used, actually. Not recommended that much, especially for new engineers. You may trip the plant because it's based on guessing. Okay, you can tune it. It's like you're tuning blindly if you don't have experience. For experienced guys, maybe that works, but for non-experienced, I don't recommend, because it's like you're tuning blindly. You're trying. So I will try this number. If performance is not good, okay, I will change, but you may somehow trip the plant. There's other methods. Okay, some are maybe complicated, some are less complicated. My recommendation, I will explain this also methodology, but my recommendation is to use softwares, to be honest, especially for new engineers, to use softwares, okay, in which you can extract the data from Pi system or DCS, and then you can model. You can identify dead time, time constant, process gain, everything. You can identify, you can draw your model and your system and your software, and then you can tune offline. You can tune offline and see the effect based on the model. See the effect. If it works fine, then implement it on the DCS, especially for sensitive loops and complex loops. If you're just immediately and you are not that experienced guy, even you're experienced, but you are not familiar with the plant. Maybe you are familiar with X plant and not familiar with Y plant. So don't take the risk and tune trial and error unless you're confident. So this is also a good tuning method called IMC, internal model control. This is basically for first order transfer functions and zero order. I haven't myself tried this on second or third order, only on first and zero. So how we calculate the proportional gain? Using this equation, 0.25, this is a constant number. We divide by process gain. We have to identify the process gain from the trend, either historian data, or if operator will allow me to do a step test, I will step the controller and see the effect and calculate the process gain. Okay. Multiplied tau into tau by theta. So tau is time constant, theta is our dead time or time delay. Multiplied CV range, like in the previous example, first example, I'm in furnace and my CV is temperature. Okay, so I have to see that temperature range, whether it is, for example, from 200 degrees to 300, for example. Okay, and then divided by my MV range, typically from 0 to 100, for example, if it is a valve. And the result of this equation will be my proportional, my optimum proportional gain. And integral will be equal to tau. Okay, I calculate tau and I use it as integral. Okay, and this is for PID, not D. But as I told you, normally derivative is not used in industries. But this is the equation for a derivative also. Okay, if you can see here for zero order ramp, integrating loops or zero order transfer function, as I told you, the only difference is R. So R is nothing by this G, which is the gain. But here, since it's zero order, it's a ramp rate. Then we have something called noisy signals. So when I'm taking, when the instrument is transmitting the signal from the field to the DCS, especially flow signals, they may have some noise. And the noise is not, you can see like noise is like this variation. And this variation is not change in the flow. It is only a noise. But it's affecting because controller will think this is a change in the flow and valve will start hunting. Okay, it will react on each change and it will start hunting, or it will not give you an accurate output because all these variations it will involve in the PID algorithm, and they are not correct. They are only noise. So we have something called filtering. Okay, noise filtering. So in the DCS system, we maybe I'll show you some after this slide. We have something called filter. we apply the filter parameter, and then the signal become steady, become clean, without these variations. So here are some typical PID values. Again, this is theory. It's a good to have a reference, but just don't take it and just implement it in the plant without, blindly. No, it can vary. But this is only something to help you to have a reference. So for flow controllers, typically proportional gain is from 0.1 to 0.5. Again, this is proportional gain, not proportional band. Okay. We can see pressure controllers 1 to 25, level 0.2 to 10, temperature 0.5 to 10, and analyzer 0.01 to 50. Integral and flow controller 0.3 to 1, pressure 0.5 to 10. Why? How can this help you? Like if you see a flow controller having an integral of 10 minutes, okay, so you can understand that there is something wrong. It's impossible to be like this, especially if it is having 10 and it's not performing well. Then you can have an indication that this bad performance because of this high integral. And you can see derivative. Mostly it's never used or it's optional. So here I can show you here that before tuning a controller, you have to detect the problem. So what you can do, take the loop in manual. Okay, you have been informed that controller is performing bad. So first thing, ask the operator if he can take it manual. Okay, if it is not very critical, he will take it. If oscillations stops, so yes, perform test on the valve. Okay, and if valve problems detected, okay, so if there is a valve problem detected, then you have to fix it. Otherwise, it's a tuning issue. Okay, so if oscillation stops in manual, that means it's a controller issue. Okay, if valve is controller is oscillating and you put it in manual, but oscillations did not stop, that means this is because of interaction of other loop. That means maybe there is upstream loop or downstream loop that's causing this issue. So detect the interacting loop. For example, you have a feed, okay, feed of natural gas going to, let's say, a furnace. So if the feed, I need to heat it in the furnace, okay? So if the feed is varying, I'm having an oscillation in the feed. So in the furnace, the temperature controller, for example, it's manipulating fuel. So the fuel will oscillate. Air, if I'm also putting air for the combustion, air will oscillate. So everything will oscillate. Everything will have a bad performance, though their controllers are well tuned. But this is because of an interacting loop upstream, which is the feed. So before tuning these loops, I have to do this step. Sorry. I have to do this detection or investigation methodology. I'll show you something before we conclude. So I'll show you this simulation here. So in this simulation, I have this heat exchanger, okay, and this is only in my laptop. It's not. I'm not using in the plant. I'm using it only in my laptop. So I have this process fluid going to the heat exchanger, and heat exchanger is heating the process fluid using the steam. Okay, so it's manipulating this valve. Okay, yeah. So what you can see here, this is our output, which is the valve. Okay, the green one. The red one is our PV. Okay, which is the flow. This is the flow of the steam, and this is the valve. Okay, so you can see it is hunting. It is oscillating. So since this is a flow controller, just a minute. Yeah. So you can see here our my proportional gain parameter 5, my integral is 3, my derivative is 0. I have no filter. So from the previous slide I showed you, it is a consistent and frequent oscillations. It is never settling down. It's never settling on the set point. So it is an indication that I'm having a high proportional gain. I can decrease, make it 1, apply, do a step change, make it 9. Again, it's oscillating. Just a minute. So again, I will have to decrease the proportional gain. It's 0.5. So you can see, though proportional gain is low, again it's oscillating. Oscillations change the behavior of the oscillations. It's not the same as before, but it's still oscillating. That means it's because of proportional and integral, both, as mentioned in the slide. You can see here, continuous cycling, high proportional, low integral, or both. Okay. So this is a low integral. Low integral means low number, that it's impatient. So I will decrease the integral, and you can see here it's in seconds. That means it's very low number. I'll make it, I don't know, like maybe 15. Apply, do a step. Yeah, and in the real plant, it will not be this fast, okay? I'm just, you can see here, simulation, and make it as fast, because in the real plant, it will take an hour or something to see the effect. Okay, so it's doing good. It's doing good. Yeah, you can see one thing here. There is a noise. Though it is meeting my set point, but there is noise. So I can put a filter, maybe 1.5. Maybe 2. Do a step. Again, there is an overshoot. Okay. Undershoot. Then it will settle.
So,
means
Engineer Umar, just to use the time as we are
well, I have
seeing this. Let's have some of the questions that have been written in the chat while
yeah
you are tuning that. So there is a question here. I'll be reading the question for you
yeah.
from Engineer Nasser Al-Alawi. From your experience, what is the most common mistake engineers make when tuning PID loops in industrial plants?
Well, there is a lot of mistakes, but one of the biggest mistake for me is to whenever you are requested to tune, you just go immediately and tune the controller. You don't understand the process. You don't investigate whether it is a valve issue, instrumentation issue. So it is not always tuning. Tuning cannot solve mechanical issues.
So you have answered his other question also. As instrumentation engineer, we face many issues during our troubleshooting, and we realize it's a mechanical issue due to a valve sticking or some cases. So how do you
Exactly.
differentiate between poor tuning and mechanical issues?
Differentiating between poor tuning and mechanical issues.
Yes.
Okay, so as I mentioned, if it is a mechanical issue, so tuning will not solve. You will not see an effect. Okay,
Okay.
so as I mentioned, if valve is having stiction, so even if you change the tuning parameters, the valve will not have a good performance. Maybe in
Great.
some rare cases it will have a good performance, but for that case, if plant load changes or some upstream condition change, then again it will the same issue will reoccur.
Great. Then resonating on Dr. Saeed Sabri question, the loops are impacting each other in some way or another. Do you take this into account when tuning each loop, and how?
Yes. For example, you have a distillation column. I want to tune the reflux flow for the distillation. So
Mhm.
a distillation column is a very interacting loops. Reboiler will interact with the reflux. Reflux will interact with the reboiler. So always I have to keep in mind that my reflux, my reboiler, my feed to the distillation, I don't always think about making them optimum only. No, I think I have to think about other loops they are not affecting. And that's not very easy, to be honest. My recommendation is to have APC for such loops and to tune loop considering other interacting loops is to have APC system.
Great, engineer. And I think with that, we will conclude our session here since we are running out of time. This is a very interesting topic, and I don't think that an hour is enough. Thank you, Engineer Omar Al Bahdoor, Senior
جزاكم الله
Process
خير
Control
وبارك الله
Engineer.
فيكم.
We really appreciate your time, and please feel free to reach out to us in ISA Amal section, especially to Engineer Omar Al Bahdoor for any further questions. This is a reminder to everyone of you to join ISA Amal section, and this is a guide on how to join us, how to be a member. So we are waiting for you all. Tomorrow, inshallah, we will continue our next session with Engineer Khalid Al-Amri, Lead Process Control and Automation Engineer from Oman LNG. He will be talking about advanced process optimization using ABC and RTO. Stay tuned. And also, we are announcing ISA Oman Women Guidance Series that will take place next week. Thank you all, and see you in our upcoming events. Yusuf Shaili was with you. See you tomorrow. Have a good night.
Thank you.